Hello everyone, and welcome to the second session of this set of YouTube sessions created to demonstrate the utilization of programming and the resulting visualizations in understanding dynamics. Today we will tackle the visualization of projectile motion. Projectile motion has two main categories: projectile motion without air resistance and projectile motion with air resistance, where air resistance is usually referred to as drag. We will confine ourselves to projectile motion in two dimensions. When the drag force is neglected, the motion of the projectile has a parabolic trajectory, in which the motion in the horizontal direction is uniform, which means that the x component of the velocity is constant throughout that trajectory and that the acceleration in the x direction is zero, while the projectile's motion in the vertical direction is uniformly accelerated due to gravity. Think of it as if the motion of a projectile has been decomposed into two independent rectilinear motions. In this way, the x-coordinate of the projectile at any instant in time is equal to the distance traveled by the projectile, and its y-coordinate is equal to the elevation of the projectile at any point in time. These simplifications cease to be valid when the resistance of the air is considered. The drag force resists the vertical and horizontal components of the projectile's motion. The higher the velocities, the larger is the drag, which renders the problem as nonlinear and introduces the need for a computational model to represent the drag and numerical methods to solve for the unknowns that were easily obtained when the air resistance was neglected. Today I am using the software Maple in order to visualize the projectile motion with and without air drag. I am using a Maple workbook rather than a worksheet or a template. In this workbook, the user is required to insert the following parameters: launch velocity, launch angle, launch elevation, gravitational acceleration constant. If air drag resistance is to be included in the analysis, then the user is required to insert a value for the air drag coefficient, which is a parameter required for the quadratic drag function. The user also needs then to insert the time discretization increment, which is required for the Runge-Kutta fourth order method to incrementally solve the nonlinear setup. The user inserts the required parameters here in this region, where for this particular example we can see that the velocity is 50 meters per second, the launch angle is 45 degrees, launch elevation is 10 meters, the gravitational acceleration constant for planet Earth is 9.81, which means that you can run this simulation on other planets if you know their gravitational acceleration constant and the drag coefficient, if any. If we set the drag coefficient in this particular example to 0 and run the Maple file, Maple will produce the required results. Starting with the right up, we can see here the flight time, range, maximum height, impact velocity, impact angle. We can see here that Maple also plots the projectile trajectory, and you can see here that there is no drag in this case. And we can also plot an animation for the projectile trajectory. If we click here on repeat and click on play, then we can see the animation of the projectile trajectory. This is the case where we have no drag or no air resistance. Now we will go back to the parameter insertion region again and change the input information to include a drag coefficient of 0.01 and run the Maple file again so that Maple can produce the required results. Again, we start with the right up, where you can see that the flight time range, maximum height, they all decreased because of the presence of air resistance. Maple also plots the projectile trajectory, but this time with drag. Maple then plots a comparison between the projectile trajectory with and without drag, and it also plots an animation of the projectile trajectory with drag. If you click here on repeat, then it will keep repeating the animation. At the end of this session, I would like to indicate that the figure or the image at the top of the Maple workbook was created using AI, and the coding required for this workbook to function properly was provided by me. This ends our session for today, and hopefully I will see you in the upcoming sessions. Best wishes.